The null space is a set of all solutions of homogeneous equations, i.e. ax1 plus bx2 plus cx3, and then not x4. Like this, and then you can put that into a matrix. A, B, C, D, E, F. And then if we multiply this by a vector, you multiply by some vector v. In this case, it would be, because this is a 3 by 2, no. This is a 2 row, 3 column, 2 by 3. So we need to multiply by something that matches this, so 3 by 1. So we would multiply by this, v1, v2, v3, and then by matrix multiplication rules, we would end up with a 2 by 1, so whatever A and B are. But because we're talking about the null space, we would be getting zeros for this. And this vector is mostly what we're trying to find, but this vector would be considered the null space of the matrix. So, for example, if we have a matrix A, and we want to multiply by some vector to get the 0 vector, how would we go about doing that? So one way is to make it a augmented matrix and then row reduce it. So when we row reduce, we get 1, 0, 0, 0, 1, 0, minus 1, 2, 0. Obviously zeros for these, but basically we have 1, 0, negative 1, 0, not 0, 0, 1, 2, 0, 0, 0. That was x1, x2, x3. And that's equal to the 0 vector. And then now we just write it out, x1 minus x3 equals 0. And then x2 plus 2x3 is equal to 0. If we say x3 is equal to t, then x1 is equal to t, x2 is equal to minus 2t, then our vector x would be equal to t minus 2t, t, or one, negative 2, 1 as a vector. The null space, null of A, is equal to the span of this vector which is a line, and it'll be one-dimensional. You can have a higher dimensional null space. For example, if we had this matrix and when we row reduce, we get this. Then we write that out, x1 plus 2x2 plus 3x3 is equal to 0. Then we solve for x1. And then let's say we want x2 to equal some variable. Let's say t, and x3 equal another variable, say s. Then x1 is equal to minus 2t minus 3s. So then when we write our vector x for the null space, we get minus 2s minus 3t. I have that backwards. Minus 2t minus 3s ts. And then we want to split this up by variable. Minus 2, 0, 1 plus t times, I have these backwards again, and then here the nullity would be 2, because now it's two-dimensional because there's two vectors. The column space, written col A, is a set of all linear combinations of the columns of A, or col A span so basically if we have m by n matrix A, then each column is a vector. Each column is a vector. In Rm. Meaning if m is equal to 2, then it's R2. If 3, then R3. The column space is a subspace of this Rm. The matrix could be seen as a transformation. For example, if we have matrix A multiplied by a vector x, the column space is a set of all possible outputs you can get from multiplying A by an input vector. To find the column space, first we write the matrix, obviously, and then identify columns as vectors. Determine which are linearly independent. and then the column space is the span of these linearly independent columns or vectors. For example, let's start with that same matrix from earlier. So we say the first vector is 1, 4, 7. The second vector would be 2, 5, 8. And the third vector would be 3, 6, 9. We want to find if they're linearly independent. So just basically put them in a matrix. And then you row reduce. So row reducing the column space corresponds to the pivot columns, so that would be this and this. So that means that we have these two. So we have 1, 4, 7 and 2, 5, 8. So the column space is a span of these two vectors. And because it's two-dimensional, this has a dimension of 2. And later on I'll talk about it, but there's this thing called the rank nullity theorem, I think is what it's called, which says that the rank of A plus the nullity of A, rank A plus null A equal to n. So n is the number of columns. The rank A is equal to the rank of the column of A. So because we had 3 columns, and then the nullity of A was 1, plus the rank of A was 2, so this is true, so we did something right.